Let me see.
Looks like you're recording it. Is it
Got
working?
it.
All right, thank you. All right, just for the purposes of the recording, I'm going to reiterate just quickly here that the point of today's lecture is to study material properties and thermodynamics for AR/VR headsets. And we're going to discuss the choices you make in materials with regards to dissipating heat and the components in there. And then we started with the zeroth law of thermodynamics, which says that heat flows from hot to cold. And in a practical example, this is a AR/VR headset, which has heat on the inside on the electronics components at about 80 degrees C. The human head is about 37 degrees C, and the air temperature outside is 25 degrees C. So heat will flow in both directions. So one of the consequences of the zeroth law of thermodynamics is that a headset will heat up your head. Okay, great. Are there any other questions about that? Okay, good. So we're going to start by discussing a few of the materials that we'll cover today. So I have sort of a little sheet here. So these are the material choices that you might use in an AR/VR headset. One of them is aluminum. Now you may not see aluminum on the outside of a AR/VR headset, but aluminum is a good material for moving heat from place to place. And aluminum is chosen in mobile devices over copper because aluminum has a lower density, so it saves you on some weight. So the number, we'll talk in a little bit about it, but the number here is called thermal conductivity, and that's how well a material conducts heat. So you can see the aluminum is about 3 orders of magnitude higher than polycarbonate, for example. The next one is polycarbonate, and that's the plastic. So polycarbonate is kind of a higher quality shapeable plastic. So a lot of those cool looking shapes that you'll see on headsets, that's often polycarbonate. It can also be high density polyethylene. It depends on the material requirements. Polycarbonate can also be transparent, but not transparent enough for optics, but it can be transparent, for aesthetics. Cotton is sort of the, not always, but an example of something textiles can be made from. So if there's any kind of fabric, it'll be similar to cotton. And you'll notice cotton has a very low thermal conductivity. And it has a similar density to plastic. And then air, so you may not think about it, but air is a great example of an insulator. So if you have an air gap in your device, that means it will stop heat flow. Now that can be good or bad. Like for example, if anybody has seen, if they've ever installed like a CPU onto a motherboard, you don't want your CPU to be contacting air because air won't conduct heat well. You always want your CPU to have a fan connected to it or a heat pipe or something like that. Silicon is not really a choice of material that we want to make headsets out of, but it's in the electronics, so it happens to be there. So silicon is actually kind of similar to glass or plastic in its thermal conductivity. It's a little bit higher density. And then glass is obviously another choice in the optical material. And then glass has a sort of an intermediate density and an intermediate thermal conductivity. Okay. So those are some of the materials we'll discuss today. Now, this is a very short lecture, so I'm not going to discuss why at a molecular level these materials behave like they do. But essentially, right, that this is an example of a metal. This is an example of sort of what are called like soft materials or plastics. And then this is a metal as well. And then this is the glass or ceramic material. Okay. So let's move on then to the first property that we'll discuss, which is thermal conductivity. So thermal conductivity is how a material conducts heat through it. So if I have a material here, and it's a material of width length, so this is like the cross section. You can think about maybe a piece of metal, or you could be looking at the cross section of a headset. But essentially, when the material here, you'll have a temperature here, and I'll put this like as a T high, that is the high temperature. And then we'll have a temperature down here, which we might call the low temperature, all right? So remember, heat will flow in this direction. And we'll indicate the heat with a lowercase q. And then what happens is that there will be a line connecting these two here. And this shows basically how the heat flows in there. Now, the equation for the amount of heat that will move through a material like this is Q equals minus K times delta T over L. And this K, sort of slope of the line here, this is your thermal conductivity. And just like in the picture, Q is what's called a heat flux. That is, it is in energy, sorry, it's in power, energy per time, per area. And so heat is expressed in watts when it's heat that's flowing, and watts is energy per time. Okay. And which is power. Okay. So then if we go back and look at our columns here, so in aluminum, if we have, say, 100 degrees Celsius on one side and 0 degrees Celsius on the other, we will push, 20,000 watts per meter Kelvin. Sorry, watts per meter in the aluminum, and then maybe we'll push, 20 watts per meter for the polycarbonate. So there's a huge difference in the amount of heat pushed through material at the fixed temperatures. Now, one of the things that people, or something that can be conceptually confusing is where do the temperatures come from on either side, right? So in all of these examples, we basically have a reservoir of heat on both sides, where even though we may be pushing an enormous amount of heat in one way or another, we won't actually affect the temperature on one side. For example, no matter what happens in your headset, the temperature of the person using it will still be 37 degrees C. I mean, unless they have COVID-19 or something, and maybe it's 39 or 100 or 40. But in general, the person's body temperature is fixed. On the other side, the temperature of the room is fixed as well. You won't be able to push enough heat that you actually cool down or heat up the room. Okay, so even though you might start using the headset, and maybe the temperature is over here or over here, but once you reach equilibria, that it's been running for a little while, you'll eventually equilibrate and have both sides fixed to the reservoir temperature. Now there's going to be an exception to this, and we'll talk about that later, but in general, basically the reservoir temperature is fixed. Okay, so does everyone understand, well, I guess, this has been like 30 seconds of it, but does anyone have any questions about thermal conductivity? Can someone confirm that I'm still lecturing?
Yeah, we can still see and hear you.
Okay, great, thank you. It's just a little bit disorienting because I can't see anyone. All right. So flux is basically watts per meter Kelvin. So it's something that occurs once you've reached an equilibration, right? So it's like after you've been running your headset for a while or you're at a steady state. There's another property of materials, and that's called heat capacity. And this describes basically how much thermal energy you can push into a material. So the equation for heat capacity is the change in internal energy in material is equal to mCp delta T, where this is the mass, This is the heat capacity. And then this is the change in temperature. Now the little p here we won't really discuss, but that means constant pressure. Everything in this, these examples will be constant pressure, so we don't care about it. But there happens to be another heat capacity defined for constant volume. Okay. So this equation is kind of interesting, I think, and that is, if you fix delta T, like let's say you raise the temperature of something by 1 Kelvin. And by the way, if you're talking about temperature differences, 1 Kelvin is the same thing as 1 degree C. Okay, so if you take a material and you raise it by 1 degree C, it turns out that it takes a different amount of energy for a different material, even with the same mass. That is, heating up, 1 kilogram of water requires more energy than heating up a kilogram of aluminum. So fixed weight, it takes more energy to heat up something by 1 degree Kelvin. So maybe some of you have heard of a calorie. So a calorie, I mean, of course you've heard of a calorie, but a calorie is how much energy it takes to heat up 1 gram of water by 1 degree C. So you notice that you have to specify water, right? It's not universal. It takes 1 calorie to heat up 1 gram of water, but it takes up, 2 calories to heat up maybe a gram of steel. I'm not sure. I don't know what the heat capacity of steel is off the top of my head. But so what that means is that if you have a headset made out of a material with a low heat capacity, then if your headset's operating with a certain amount of joules now, so we're talking about energy, right? So this is not per time, this is just over a short amount of time, then you will raise it a certain amount of temperature. Hi, Rowan. That is lecturing. So let's take a look at some of the heat capacities for materials. Yeah. So heat capacity for aluminum. Yeah, I'm right here, son. So heat capacity. My iPad. Yeah, you can have the iPad. Here you go. Go play with the iPad. So if we have aluminum, the heat capacity is about 0.9 joules per gram Kelvin. Whereas if we look at something like cotton, it's 1.34 joules per gram Kelvin. So if you were to make your headset out of 1 kilogram of cotton, then it would take more heat to heat it up 1 degree Kelvin versus if you made your headset out of aluminum. So that's kind of interesting. So that it's kind of balanced out though, because aluminum is much more dense than cotton. So a 1 kilogram headset made out of cotton would be enormous, and a 1 kilogram headset made out of aluminum would be small. So it can be somewhat unintuitive because you might think, oh wow, 1 kilogram of aluminum might require a lot of energy to heat up, but actually it doesn't. But the thing is, 1 kilogram of aluminum will be smaller than 1 kilogram of cotton. Okay, no, don't buy that. Yeah, why don't you go have mommy help you watch Big Dog, okay?
Where did you find that?
I was using it for a calculator. Sorry. Okay. So that's an overview of heat capacity. So heat capacity, like I said, is something that hopefully we don't run into. In general, we hope that we're operating at steady state so that everything is at sort of a fixed temperature. We'll discuss, if we have time, a little bit about how you can use heat capacity to adjust or to sort of load balance. Like if you need to operate your GPU at a very high temperature for a little while, you can maybe use heat capacity to sort of cheat and spread that power dissipation over a little bit of time. Okay. So that covers sort of the main properties of materials that we'll be thinking about. So there's density, which I didn't discuss, but I hopefully you're all familiar with density. That's just how much mass it requires for, or how much mass the material is for a fixed volume. Then thermal conductivity, which is where we get a lot of variation, and then heat capacity. Okay. Let's remind myself. So we talked about heat capacity and conductivity. Ah, yes, now we must discuss convection. Okay. So when we talk about heat transfer, that is how heat moves between matter, it occurs through three mechanisms. Okay. One mechanism is conductivity or conduction. And that's what we were just discussing. Conduction is what happens when you have two materials in contact and you have, or not two materials, if you have a material with a temperature on two sides, conductivity describes how heat moves within the material. Then the next kind is something called convection. And convection is mathematically the same thing as conduction, but what happens is that convection occurs on a very small scale, and as it's conduction on a very small scale, but it involves a little bit of fluid dynamics. So if you have, like, say, you know, maybe a hot cube, okay? Well, nobody has a hot cube. Pretend this is a cup of coffee, right? Well, what happens is that you'll have these little air currents that will develop on your coffee, and they will dissipate heat through the air. So it is at a molecular level like conduction, that you have hot liquid contacting with the air, which causes the air to absorb some of the heat. But because it involves these convective currents, like flow of fluid, and also evaporation, we have to approximate it using an empirical formula, which we'll discuss in a moment, and that's convection. And so anytime you have heat transfer through a medium, be it air or water, it's always described by convection. Okay. So conduction is sort of contacting materials. I should say contacting solids. Convection is solids and liquids with a medium, and that medium can be just something which it's immersed in, a fluid which it's immersed in, and a fluid can be a liquid or a gas. And the last one, which we won't discuss at all, is radiation. And it's confusing that the radiation means, you know, both for temperature and for you know, nuclear radiation. But radiation is how the sun heats up Earth, right, through photons coming at Earth. But one of the fascinating things about radiative heat transfer is that it scales by temperature to the fourth power. So it actually completely dominates at high temperature, but at low temperature, it actually has almost no effect. So we won't really see radiation as acting on our AR/VR headsets. Okay, so if we go back to our picture, then we will have thermal conductivity governing everything here, but then when our AR/VR headset tries to dissipate heat into the air, it will be through convection. And convection is actually described by a very simple formula by, you know, the one, the only, the OG Isaac Newton, and that is Newton's law of cooling. Newton's law of cooling says that the heat flux is equal to H times the temperature difference. And H is a system specific heat. I'm going to call it a heat. God, I can't even write. Heat transfer coefficient. Heat transfer coefficient. All right. So again, this is a flux. So this is per unit area. So it can also be written like this: Q dot equals HA delta T. So here we're talking about something in watts. The dot means it's per time. And here we're talking about per area. So all I've done is move the area to the right side. Now, this equation actually is so important, and I don't think most people understand it, okay? So like, let's say that you have your house, okay? And draw a house here. That's the house, all right? And you have a heater inside the house, right? And then you know, this is my heater or something. I don't know what heater in this cartoon house looks like, okay? Electricity comes in here, and then I pay out dollars, right? For my heating bill. So let's say that you keep your house at, I don't know, 65 degrees in the winter. You know, you're very good at saving energy. And let's say outside it's, I don't know, say 40 degrees Fahrenheit. Okay. So then if we think about the amount of heat that we have, we're going to have Q dot equals HA times, I'm just going to leave these unspecified, times 65 minus 40, right? So this is going to be Q dot equals HA times 25, right? And Q dot is the same thing as money, right? When you go pay your bill, you pay in watt hours, which is a unit of energy. So I guess we need to multiply by like how often you use it, but we won't worry about that for now. Then let's say that we have another person who likes to keep their thermostat at 75 degrees, okay? So this is a very cold person, right? So then if you look at the Q dot here, it's going to be HA times 75 minus 40, right? So Q dot equals HA 35. So a 10-degree difference here makes, right, almost a 30% difference in the amount of energy required. So I think that's a little bit unintuitive. Basically, it says that, right, even though you're making, you know, a 10-degree difference, and it's, you know, 65 degrees to 75 degrees, which relatively speaking is not that big of a difference, right? 65 to 75. But that actually is, you know, I guess if we think about it as 25 to 35, that's almost a 50% increase in your energy bill. So 10 degrees leads to 50% increase in energy. So Newton's law of cooling is actually a pretty important thing to keep in mind. Now let's talk about then a headset, right? So if we're thinking about our VR headset, when it's contacting the air, right? So this is the air, and we have our convective currents off of our headset. If we make our VR headset have a temperature of like 40 degrees Celsius, so that would mean that the headset, if you touch it, is a little bit warmer than a human body. Versus if we make it 50 degrees Celsius, 50 degrees Celsius, right? This is now not scalding hot, but pretty warm. It would be uncomfortable to hold it for a little while. The difference in energy, right? This is the air is 25 degrees C. So the amount of heat we can dissipate here is 15 degrees, is delta is 15. Then here the delta is 25, right? And this is like, you know, almost double the heat difference. That is, we can dissipate almost twice as much heat by operating at 50 degrees Celsius. So if you want your headset to dissipate twice as much heat, and remember, dissipating twice as much heat means you can have twice as much of a CPU or twice as much of a GPU in there, right? So this is the difference between, like, you know, a CPU operating at 2.5 gigahertz to one operating at 5 gigahertz. It's a double difference, only from moving by 10 degrees Celsius. So it's a big effect. So the operating temperature of your external surface on your AR/VR headset really determines almost everything in the thermals. Now, I should mention that 60 degrees C, this is kind of like almost scalding. I think like 67 degrees Celsius, this is like when you need to go to the doctor. Ouch. Okay, so you don't want to get up to 60 degrees C, 67 degrees C, 70 degrees C, that's too hot. Okay, so that is a quick overview of Newton's law of cooling. Hopefully we'll have a little bit of time to apply it, but are there any questions thus far? All right, can someone just confirm to me that I'm still in the Zoom room?
Yep, still can hear you, yes. Can still see it.
All right, great, thank you so much, guys. Sorry about this. My power is now back on, but I think I don't want to take the time to switch over to my computer quite yet. Okay. So going back to our goal here. So convection is not a property of materials. It is just something we need to keep in mind when we think about the thermals. Okay, so there is no intrinsic thing for the properties. Oh, I should mention something, is that if you want to know the heat transfer coefficient, it's actually quite a complex equation to look them up because they're all empirical. But I will just mention that they depend on the density of the fluid, like if you're in water or air. They depend on the pressure. Right, if you're in water, if you go deeper in water, the pressure matters a lot. But in air, you know, typically, unless you're on top of Mount Everest or something, the pressure doesn't change that much. But maybe if you're looking like a rocket ship or something like that, that will matter. Or if you're doing AR/VR headsets in space, that might matter. It also depends on the Reynolds number, which basically means, is your air flowing or not? So if you put a fan on your headset, that will make an enormous difference. And it actually depends weakly on temperature. So H is itself a function of temperature. In practice, you don't need to worry about that. You just sort of put the average temperature of the delta T in for H, and that's okay. But just to give you some perspective, like H is about maybe 2 for just a plate and air, which is what we'll model our system for. It goes between 2, which is maybe around 0 degrees Celsius, up to about 5, which is maybe around 50 degrees Celsius. So it does change quite a bit, but it's usually you know, not that big of a deal. And the units of that are in watts per meter squared Kelvin. Okay. And you know, if you're really doing some careful engineering work, you can look up specific correlations for your system and get a heat transfer coefficient. Now we need to just introduce a few miscellaneous parameters. So the first one is how much heat do we get in a AR/VR headset, right? So it turns out in an AR/VR headset and in any computer environment, and actually any electronic, all of the power input to the device from the battery or from the power supply is converted into heat, 100%. You may be thinking, oh, you know, when you're wearing an AR/VR headset, don't you get like some photons coming out of the display? Well, yes, but they are so little energy in the photons and they go directly into your face, which means it's essentially like putting heat back into the system. But yeah, computers operate at like, you know, 0% efficiency because the output of a computer is going to just be a calculation, which ends up as being heat, right? You're just moving bits around in your hard drive and your RAM, and that doesn't actually, you know, give you any usable energy. So all electronics go 100% to heat. And that really simplifies our analysis because then we know, if we know how big our battery is and how much power is coming out of our battery, then we can compute how much heat we have to work with in our system. So let's take a look then from the battery. So a typical battery for a mobile device, like an AR/VR headset, is usually measured in what are called milliamp hours. And they usually go from 1,000, which is sort of a smaller battery, milliamp hour, to maybe about 7,000 milliamp hour. And a 7,000 milliamp hour battery would be an enormous cell phone battery. Does anybody, does anybody know, does anyone have a 7,000 milliamp hour battery? I want to know so I can buy that phone. No? Okay, I think like an iPhone 11 is like a 3,000 milliamp hour battery. Now, are there any electrical engineers or computer engineers in the class?
Yes.
So can you tell me what is weird about measuring battery capacity in milliamp hours? What is unusual about that?
It's really not a whole lot of capacity.
Well, I guess what I'm after is what is an ampere? What does that measure?
The amount of current.
Right? And then we have hour, right? So what does current times time give us?
Charge.
Right. And I guess charge is kind of a strange unit of measurement, right? Like you wouldn't know how many joules there are in a battery if you only know the charge, right? What is the missing component in this? It's okay if you don't know it.
I don't know, to be honest.
It's okay. It's voltage. Right? What is the voltage? So if we wanted to know the power in a battery, it's equal to the current times the voltage. And if we want to know the energy in a battery, it's equal to the power times the time. So we know the time, it's an hour, right? And we know the current, it's milliamps. We don't know the voltage, okay? And I find this to be so fascinating, is that it just turns out that everyone defines the voltage in all embedded systems to be 4.2 volts. Does anybody know what's special about the number 4.2 volts? I'll give you a hint. It won the Nobel Prize last year, 2019, from this guy named Goodenough. What a great name, huh? He won the Nobel Prize. He's Dr. Goodenough. All right, that's okay. So I just got a notification somebody left the room. All right. Sorry about the hard question. So this is actually the voltage of a lithium-ion battery. So lithium-ion batteries are so standard in all mobile and embedded electronics that everyone just assumes that that's the operating conditions for them, that it's always going to be at 4.2 volts. So it's just implied. It's a strange thing, but everything is measured always assuming 4.2 volts. Can someone remind me what time this class ends at?
3:15 would be, I think, the end of the end of the scheduled time. Is usually it's an hour and 15.
Thank you. Okay. So then if we wanted to compute the amount of power in these batteries, we would need to take the current. So let's just start with a small one, 1,000 milliamp hours. And then we would multiply it by the voltage, which is 4.2 volts. Okay. And amperes times volts gives us watts. So this would give us 8.2 watt hours. Okay. So I dropped the milli because we're in thousands, right? And then 8.2 watt hours. So an hour is 3,600 seconds. So this would be, I think, 2.5 kilojoules. My son took my iPad, which is my calculator, because my computer's off. Let me just quickly go through this here. So 8.2 times 3.6 times 10 to the 3 equals 24 and change. 25 times 10 to the 3 equals 25 kilojoules per 25 kilojoules. All right.
Why is it 8.2?
Oh, no, because I think 1 times 4.2. Oh, you're right. Why is it 8.2? Sorry. I'm going to adjust this so that my notes are consistent. Okay. Sorry. Let's go with that. All right. That should be close enough. All right. We'll just go with that. Yeah. Why is it 8.2? Good question. Okay. So there you go. So maybe on the order of 25 kilojoules. All right. So that's sort of what you get in a battery. Now, we don't actually want to know about the energy. We wanted to know about the heat. And remember, heat is measured in watts. So let's go back to here. So if we're 8.4 watt hours, then that means that we will be using about 8.4 watts. Sorry, if our battery has a run, okay, so let me think about how to say this. We will need to dissipate 8.4 watts per hour when we're using our battery. Sorry, 8.4 watts. Yes, that's right. Yes, so we will be kind of working at about 8.4 watts. So I looked up an example of one here. So the HoloLens 2 says it has 3 hours of runtime. And its chipset is a Snapdragon 850, which operates at about 2 watts. So just by extrapolating, we can see that probably the battery in the HoloLens 2 is maybe about a 9 watt-hour battery. Based on the fact that, you know, if our CPU is taking up 2 watts, we maybe need about 1 watt for the rest of the device, for the display and for the memory, and for any sort of thermal losses. This HoloLens 2, maybe then going back to our equation here, maybe has a 2200 milliamp hour battery in it. Okay. So I think then, you know, this is a good number to keep in mind, is that in sort of our AR device, we can assume that we are going to be using about 3 watts of power for our system. And 3 watts is then the thermal energy being generated in our device, which needs to be dissipated. Now, of course, when we're running an AR/VR headset, we may boost, you know, on our CPU and need to generate more heat, or it may be that we're doing something that requires very little computation, and so it goes down. But I think 3 watts is about a good approximation for how much heat we're going to need to dissipate. All right. So up here, right, so like, for example, if we have an 8.4 watt-hour battery, and then let's say our device, we think it will use all of that up in 2 hours, then we would have 4.2 watts needing to be dissipated. But maybe our device runs for, you know, maybe it's like a phone and it runs for 12 hours or 16 hours. Then we would only need to dissipate 0.5 watts, right? So it depends on what our target lifetime is for our device for how much heat we need to dissipate at any given time. Okay, so the point is that all of the heat that we use from our battery is dissipated. So if we look at how long a device is supposed to run and the capacity of the battery, and knowing that the voltage of a lithium-ion battery is 4.2 volts, we can calculate how much heat needs to be dissipated out of our system. And as a specific example for the HoloLens 2, I would estimate maybe 3 watts would be the budget for heat that needs to be dissipated through the headset. All right, are there any questions on that? Okay. So moving on, let's talk about a human body, because it may be relevant. So a human body, okay, is about 2 meters squared of surface area. Don't ask me how people found this out. It will be very gross, but don't look at the research papers on it. In a human body, like an electronic device, dissipates about 99.99% of what it eats as heat. Now, an exception to this might be like a child, which is growing. And so maybe 1% of the amount of food they eat is turned into matter. And maybe if you like to exercise, then maybe 10% of what you eat per day goes into locomotion. But remember, when you run outside, you are highly inefficient and you actually don't create any work because you go back to where you started. So pretty much all of that goes to heat. But some of it goes to sound, right? Some of it goes to friction, some of it goes to wearing down the road, things like that. But in general, about 99.99% of all of the food you eat is dissipated as heat, okay? So how much food does a human being eat? Well, we'll say about 2,000 calories. Now, these are dietary calories. So these are actually kilocalories. So you eat 2 megacalories per day. That's how much you eat, and that's how much you dissipate. And then a calorie is 4.184, so we'll estimate this as about 8 megajoules. So although I wouldn't recommend it, you can see that if you ate about, 32 cell phone batteries per day, you could use that instead of eating food. That's just a joke. You can't eat cell phone batteries. But just thinking about the energy difference, there you go. Now, if a human being generates 8 megajoules of energy per day, then how much of that is actually heat? So we need to divide this by the amount of time in a day, which is 24 times 3,600 seconds, which equals, I think I calculated this. I hope I calculated this. I did not calculate this. Can somebody tell me what is 8 megajoules divided by 24 times 3,600? Oh, no, I did calculate. I think it's about 100 watts. So that is the amount of heat that you generate constantly, right? So it's energy per second. So you're generating 100 watts. So for reference, like a power supply in a PC is maybe 300 to 500 watts. So every second you need to push 100 joules, so 100 watts of heat out of your 2 square meters. And out of those 2 square meters, about maybe 3% is on your forehead and your eyes. So for a AR/VR headset, you will have about 3 watts of heat coming off of your face, or 3 watts that wants to come off your face. However, as we saw, you do not actually, your headset won't actually accept the heat because your headset operates at a higher temperature. But you've essentially pushed 3 watts or so of heat out of the normal region, and it has to be dissipated elsewhere on your body. Okay. So if we go back to our figure then, let me find the figure of the headset, we now see that we have essentially 3 watts on the head side of heat that we want to push out, but has to be pushed out into other areas. And then we have 3 watts that we have here that we want to push out either onto the head or out through convection. Okay. So is everybody following? Are there any questions so far? And don't be afraid to ask, simple questions. I know a lot of you are from a different background, so this maybe makes no sense to you. Or maybe you've never seen a watt. Please don't be afraid to ask. Okay, can someone confirm that I'm still lecturing? Great. Okay.
Sounds good.
So now we are going to look at a little bit of an energy balance. As soon as I find my notes. Okay. So the first thing to consider when designing an AR headset is can you dissipate the amount of heat generated from your battery safely? And this determines essentially what kind of a chip you can use, right? So like I said, batteries can go up to 7,000 milliamp hours. Like you can put a gigantic battery into a headset. But if you can't dissipate the heat, then you can't put a battery that big into it. So the heat dissipation actually determines a lot of the power of the electronics that can go into your headset. So let's take a look at that. So the determining factor is convection, right? Because that is sort of the output from your system, is the convection from the headset to the air. So this is our headset. And essentially you dissipate, right, as a plate. Now, of course, you can have like a curve here, right, or something to try to increase your surface area. And if you look at real headsets, they aren't really a plate, but essentially we can approximate it as a plate. And then any kind of curvature added to it just sort of increases the surface area. So if we now look at a cross section of the headset, so I sort of unwrapped a headset as a flat plate. The first dimension is sort of how wide they are. So the circumference of a human head is about 55 centimeters. If you imagine that a headset will sort of wrap around to your ears, you can maybe estimate it to be about 25 centimeters wide. And then how thick is a headset? Well, that's something that, it depends on the headset, but let's say it's about 10 centimeters. And 10 centimeters is a little bit high, but let's say the 10 centimeters accounts for the fact that the headset is usually a little bit curved outwards to increase the surface area. So then the area of a headset is about 250 centimeters, which is 0.025 meters squared. Sorry, this is centimeters squared. Okay. Then if we go and look at Newton's law of cooling, we have that Q, the heat flux, is going to be equal to H times delta T, right? So the heat flux, as we saw, our goal is to dissipate 3 watts, and the flux is per area, so 3 watts per 0.025 meters squared. And then the heat transfer coefficient is about 5 for a plate in this setting, and natural convection, natural meaning that there's no blowing of air, watts per meter squared Kelvin. And then our temperature difference is going to be the temperature of the device, which I'll mark as TD, minus the temperature of the air, which is 25 degrees C. Okay. So if I compute this out, which is going to be very difficult without a calculator, can somebody solve for TD quickly while I turn on my computer? All right, maybe I can just do it in my head here. So 3 divided by 0.25 is 12. So this is 120 watts per meter squared. Equals 5 watts per meter squared Kelvin. TD minus 25 degrees C. So if I divide 120 by 5, I get approximately 25. Call it 25. Equals TD minus 25 degrees C. Okay, so we get that we should be approximately 25 degrees C difference, so that's 50 degrees C. So with about a 10 centimeter height difference there, we can dissipate the heat, assuming we have a temperature of 50 degrees C. So I think that's a little bit high. I mean, for comfort level, I think we would aim for a little bit lower. But that is something that, you know, you have to think about or balance with your design constraints. But now notice that is that it's 50 degrees C. Now let's say that, you know, if we increase our watts from 3 watts to even higher, then essentially we're ending up, like, let's say we go to 3 watts to say 5 watts, this is going to go up to almost, you know, 70 degrees C, which is scalding hot. So we can't do that. That's too hot. That would hurt people. So looking at this problem setting, can somebody tell me another way that you could increase your battery size and your computing budget by changing a different variable rather than the 50 degrees C? What else could you change in this problem setting to improve your power? I didn't quite catch that. Just heard static from you. That's a lot of static. Okay, Jiakai? I think I might mute you. Okay. Sorry, Jiakai. I don't know what's going on with your microphone there. Does somebody else have an idea of how we could adjust this problem? Okay, so one way we could adjust this problem is that I only had the headset wrap around to my ears, right? I could try to wrap the headset all the way around the circumference of the head. That would double the surface area, right? And that would double the available heat dissipation, right? It would have our heat flux. So that's one thing you could do, is by making the device go all the way around your head, you could increase your battery size by almost, 50%, or sorry, by almost 100%. So somebody say, wow, right? That's fascinating, right? Like, you probably thought in this lecture that, wow, who cares about heat conductivity or thermals? But I'm showing you here that by knowing this, you know how to increase your battery size. You can double it by being smart about how you design your headset, right? Cool. Well, I'll just assume you all are saying wow to yourselves. Okay. Other ways you can increase it, you can add active cooling. You can put a fan in it. Nobody likes that though. Another thing you might try is you could hi.
Hi.
What was that?
I got my dog up there.
No, I'm still working a little bit longer.
Mama, Dada.
Just a little bit more. Rowan, can you go read a book to Siggy? Rowan, can you go get your Big Dog book from your bedroom and read it to Siggy? Thank you. Okay. So I think we have time for one more example. Oh, I'm sorry, Rowan, I can't read that one right now. Read it to Siggy. Sit down. Siggy, down. Siggy, down. Okay, go ahead. Read to Siggy.
Dada.
Oh yeah, I'll read this one. Thank you. Can anybody still hear me?
What's that?
You're doing good.
Yeah, okay, great.
What's that?
Those are my friends. Dad is talking to his friends.
My dada, my dada.
Yeah, I know. I'm still your dada. Okay, the last one I want to talk about is how thermal conductivity plays a role. So if we're designing, yeah. So if we're designing a headset, and we think about
My dada.
here, Rowan, you want to here have a piece of paper, and why don't you draw your own lecture notes on it? Oh, sorry, I'll be right back, guys. Oh, I know. I'm sorry. You come in and see Okay. Right. So right. So designing the materials that we use in it. So the heat will be generated in the center of the device on our silicon. So this is where our heat generation occurs. This is where our 3 watts is coming in. So we want to operate at about 80 degrees C, maybe less. I don't know. It depends on the device. Now on this side, which is the head contacting side, we really want our temperature to be maybe around 40 degrees C. 40 degrees C will give us sort of a low, so this is going to be 37 right over here, but our device will be at, say, 40. This is going to give us a low temperature difference, so we're not pushing too much heat into the human. So we're not pushing that much heat here. So this is hopefully low by having 2 to 3 Celsius difference. So to get from 80 degrees C down to 40 degrees C in a small distance L, we need to have an example of an insulator, right? That is that it will have a big temperature drop across the L. So let's see an example. Like let's say we took let's look at our equation. So sorry guys, I lost my train of thought here. Okay, let's start on this side actually first, and then we'll go to the other side. So here we want to push as much heat as possible through here. And then, our goal was to be at 50 degrees C here. So we want to be at 50 degrees C here, we want to be 80 degrees C here. And let's say that we have about, I don't know, maybe 2 centimeters to work with. So let's just compute what would be the K, the thermal conductivity we'd want for this part of our device. So Q equals K times delta T divided by L. That was our equation for thermal conductivity. There's a minus sign here, but it doesn't matter. Just remember that heat goes from hot to cold. And then the minus sign doesn't really make a difference. Okay. So again, we have 3 watts per 0.025 squared centimeters. And that equals our thermal conductivity, K, which we're solving for, okay? And then our temperature difference, we want to be about 30. And we want it to be 30 over 0.02 meters. Sorry, this is meters squared. I already converted it meters. Okay. And this 30 is measured in Kelvin. Okay. So I said that this is 120 watts per meter squared. Is that what I said? Yes. And then we will multiply it by 0.02 meters, and we will divide it by 30 Kelvin, and this will equal K. So 0.02 is going to be So 0.2 would be 24. So 0.02 would be 2.4. 2.4 divided by 30, so that's 2.4 divided by 30 watts per meter Kelvin equals K. So what is this? This is like 2.5. Man, okay, maybe we'll do it this way. So this is
0.908.
What is it?
It's 0.08.
Thank you. Thank you. Equals K. All right, so let's go to our material properties, okay? We'd like to have about 0.08 watts per meter Kelvin. So it looks like we could get close-ish with polycarbonate or cotton. Now let's think about this. So notice that the delta T for fixed delta T, sorry, not for fixed delta T, but if our K goes up, right? So that if K goes up, that means we have a more conductive material. For a fixed heat capacity, our delta T goes down. So that is, if we picked like aluminum, then our heat over here would be like 80 degrees C. That is, as this goes up, this goes down, right? So if we want to hit the polycarbonate, like we want to have that polycarbonate be our material, then we would need to add maybe 1 more centimeter here. So maybe we would go to 3 centimeters. So a little bit more than 1 inch. And that would get us our desired target. So then maybe we could get the polycarbonate here. So I'll just put the polycarbonate. Okay. Now let's go to the other side right here. So here we want to have an even steeper temperature drop, right? We want to get from 80 all the way down to 40. But on the other hand, we don't want to push as much heat, right? We want to maybe only push 1 watt, maybe even half a watt towards the person. So then if this is going to go down, and we have approximately the same delta T, then our K needs to go down, right? So then on this side, if we need our K to go down, we would choose the lowest thermal conductivity, which is cotton, or maybe even air. We might even add a pocket of air onto the device. So how do you add a pocket of air? Well, it's a good question. So if we have our device like this, we're looking at the cross section, what we can do is that if this is the hot side, and then this is maybe a little bit of cotton, like the textile, this is the cotton here, we might use plastic pieces like this. And these little plastic structural elements are like pins, and they will have such a small area that very little heat can flow through them. So a very small area, so very little heat can flow through them. And this will essentially mean that all of the heat transfers through this air. Okay. So we can get the low thermal conductivity. Sorry, guys. My son really likes me, and he's really excited I'm home today with him, but I don't have a lot of time with him.
It's okay.
Okay.
It's really cute.
Thanks. Yeah. All right. So you can try to cheat and put air in there, but I think most of the devices will probably just put textile there. So when we think about the materials that go into this, we can see that we can use polycarbonate here. Here in the 80 degrees C operating range, we can have silicon or maybe aluminum. And then here on this end, we will have our insulator being the cotton. All right. And then with what I've described here, the final numbers will look like about maybe 2.5 watts going that way, and about 0.5 watts going that way into the person. And I actually don't know the biomechanics of how much heat a human being can dissipate, over their forehead, but I think that you can probably have about a 0.5 watt going into your head and still be okay, be comfortable. You might get sweaty though after a little while. Now, how would we improve this? You could improve this. You could do this, what I suggested here, by putting an air gap, and that will cut that down for a fixed, temperature gradient. Now you may be thinking, hey, why not just put a really big insulator so that it goes all the way down to like say 32, and then now you're cooling the head. Well, the problem is that then in your expression here, the sign switches because now heat is flowing the other way. And then you would need something with a negative thermal conductivity. And there's no such thing as a negative thermal conductivity material. So you have to always have it be high enough so that you get that 0th law of thermodynamics pushing the heat over, right? So no matter what you do, it's got to be above the contact temperature of 37. And I think 40 is a reasonable, number to shoot for. 40 would not be that uncomfortable. Okay, I think I'm going to stop it there. The key point I want to get across is about these material properties, right? So we saw that we can use aluminum if we want to have high conductivity. Polycarbonate is something which we want to use because it forms nicely and it's cheap. And it does have, thermal conductivity that we can use. Cotton is good to contact the human body, not only because it's comfortable, but also because it's an insulator, right? Air can be used if we can make pockets in our device. And silicon is something just which exists in our device, and glass is the display. I didn't really talk about that too much, but it's just another material we can have in there. And we didn't really talk about heat capacity, but essentially, if you're operating dynamically, like if your load goes up and down and up and down, where this is the CPU draw, the CPU power, then you can actually have this problem where if you have too little heat capacity, then your temperature will follow this curve. But you can basically add a little bit of aluminum, or maybe the silicon is enough by itself, it depends. And that can sort of dampen out this, right? Because the more heat capacity, then the more energy, the more heat it takes to raise the temperature in your device. So by adding, a little bit of heat-soaking materials like the aluminum or the silicon might be okay, or maybe it's okay with the cotton or the polycarbonate, you can sort of absorb some of that load so that even though your power draw might go up and down during the device, you maybe don't have your temperature going up that much higher. Okay. So I think that's all I want to cover. I'll go ahead and open it up for questions then. So I think there will be a small assignment, a couple problems. I think most of the equations and the mathematics is very simple. Most of the work in these equations is sort of doing the unit conversions. So I think as long as you refer back to those two simple equations we had about heat capacity and thermal conductivity, and I'll restate them on the homework assignment. It shouldn't be too difficult. I think the only really conceptual thing you need to remember is that heat goes from hot to cold, and then you don't have to think about signs or which way the lines are facing or the orientation. It's all pretty straightforward. Great, so thank you for bearing with me. I know this was a challenging lecture with a power outage and my son interrupting us, but I hope you all learned a little bit about materials and heat transfer. So you can catch me via email if you have any questions. And I think that's it. So thank you, everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.
Bye.
Bye.
Thank you so much.